All right, we are back for the second half, Monday, October 5th. And in the first half, we introduced the Catalan numbers as the solution to this counting problem. And we gave a proof for the formula for the Catalan number, which you can write in many different ways. I guess the version that we proved is this one. And I should say that if you look at the handout on the Catalan numbers that my colleague Dennis White wrote that's linked from the syllabus, it's going to give you many other interpretations for the Catalan number besides this, counting the number of paths that stay weakly above y equals x from 0, 0 to n. It talks about a whole bunch of other combinatorial objects that you can prove are in bijection with these paths. These paths are sometimes called Catalan paths. They're sometimes called Dike paths. There's a whole bunch of names for them, but there are many other interesting combinatorial objects that are also counted by the Catalan number, which is why they end up being so popular. Any questions before we move on to Fibonacci numbers, which are also popular? Just gonna flip to the next page here. Okay, that was our proof. I used this interesting bijection, this reflection for the bad paths. Any questions I can answer about that, how this proof went before we move on? That was the end of our proof. Okay. So let's move on to chapter 4, which is Fibonacci numbers. And Fibonacci numbers, they come up in nature. They're somehow very interesting. Just as I said that people love the Catalan numbers so much so that my advisor wrote a book called The Catalan Numbers. There's actually an entire mathematics journal called Fibonacci Quarterly, which is just about Fibonacci numbers and things related to them. There's just a lot of cool stuff. So they're an example of a couple of things, but first of all, you're given some interesting numbers or a sequence of numbers just by a recurrence, initial conditions, and then a way of generating new ones. Sometimes a sequence of numbers comes to you via a recurrence. And initial conditions. Okay, so as in, so Fibonacci's recurrence goes like this. It says he wants to create a sequence of numbers f sub n that satisfy f. So it's going to be capital F sub n. Well, you want to get the next one, f sub n plus 1. You take the previous one, f sub n, and you subtract the one before that, f sub n minus 1. This is going to be valid for n greater than or equal to 1 because they start at f sub 0. So the initial condition tells us f sub 0 is 0 and f sub 1 is 1. And we do need two initial values, f0 and f1, because the recurrence already starts out asking for two values, n and n minus 1. So the first time you can use this recurrence is when n equals 1 to get f sub 2 is f sub 1 plus f sub 0 is 1 plus 0 is 1. And I'm just going to tabulate some more of them, leading to a tabulation. No, that's not how you spell tabulation. Tabulation. All right, here's n, f sub n. Maybe I'm going to do this in a few columns. I don't know. I don't have that much space in this page. 0, 1, 2, 3, 4, 5, 6, 7. How far am I going to go? I think I'm going to go up to 15. N, f sub n. Just to illustrate some points. 8, 9, 10, 11, 12, 13, 14, 15. Okay. So let's get a few of these. So we said at the very beginning, right, we were only given to start out the f sub 0 and f sub 1, and they were 0 and 1. And then to get the next one, f sub 2, we just said, oh, take the previous two and add them up. So we add 0 and 1, and we get 1. To get f sub 3, I add the 1 and the 1, so I get 2. To get the f sub 4, I add the 1 and 2, so I get 3. And it's looking like it's 1, 2, 3 for a while, but that's not going to be the way it goes. It doesn't go 1, 2, 3, 4. Next one is going to be 2 plus 3. F sub 5 is 5. F sub 6 is 3 plus 5 is 8. F sub 7 is 5 plus 8 is 13. Next one is 8 plus 13 is 21. Let's see, 21 plus 13 is 34. Next one is going to be 55. Next one is going to be 89. I'm just adding the previous two to get the next one. Okay, I'm going to stop trusting myself to get these right because I make too many mistakes. 233, a 377, and a 610, and it keeps going, and we're going to stop there. Okay, so those are the first, say, 15 or 16 Fibonacci numbers. Everybody good? And because people have been staring at these things for so long, I actually forget which century Fibonacci was in, but it's many centuries ago. It's like so yeah, if somebody can look that up for me on Wikipedia. Fibonacci lived in Pisa. I think his name was Leonardo da Pisa, Italy. And I want to say it was like 1300s, 1400s, 1170. Oh my gosh. I read the 1170 is 1770. That is a heck of a long time ago. So people have been staring at these numbers for a while, and they like immediately notice things. So actually let's notice, first of all, I'm going to add another column to the table, whether they're even or odd. So I'll write E for even, odd for, or O for odd. Let's see, so 0, that's an even number, right? Yeah, so I should be writing E, not what I was about to write. E, 1 is an odd number. O, 1 is an odd number. 2 is an even. 3 is an odd. 5 is odd. 8 is even. 13 is odd. 21 is odd. Even, odd, odd, even, odd, odd, even. And so you start to realize, it's looking like it's going even, odd, odd, right? And so that's like one of the first things people notice about them, and it's not hard to prove. So why do people like Fibonacci numbers? Whenever you notice something that you think is true about them, and there is so much that people have noticed, it's usually easy to prove using induction because it's been defined by a recurrence. You just have to use the initial conditions or some initial conditions. Maybe you have to go a little ways, check your assertion, and then try to prove it for the next case using the recurrence. So let's prove that. Even, odd, odd. Yeah, so what is actually the proposition? It's even when your subscripts, which one's the even ones? It's the 0th, the 3rd, the 6th. So it seems to be even when you have f sub 3m, and it's odd when it's f 3m plus 1 or 3m plus 2. Everybody see that? It's when the subscript is divisible by 3 that it seems to be even. Okay? The other ones are odd. So let's try to prove that. We guess this proposition. F sub 3m is even. F sub 3m plus 1, F sub 3m plus 2 are odd. Okay, Everybody see the formulation there? And the proof is easy enough, you know, induct on M, say. And really, there's actually three assertions, right? For each value of M, we've said three things, right? That this one's even and these two are odd. But still, we can check a base case. Base case, M equals 0, is still easy to check, even though there's three assertions. F sub 3 times 0 is F sub 0. Well, that's 0. Yep, even. Check that. And F sub 3 times 0 plus 1 is F sub 1. That was one of our initial conditions. Yep, that's odd. And then F sub 3 times 0 plus 2 is F sub 2. That was the first one that we had to calculate via the recurrence, but we did calculate it, and it's a 1 and it's odd. By the way, that's a 1, not a 7. Sorry, that's a 1. Okay. And then in the inductive step, we just assume it for smaller values of M, and we tried to prove it for the next one. Say like, you know, I don't know. You can either phrase it, we assume it for M and all smaller, and we try to prove it for M plus 1, or you can phrase it, we're trying to prove it for M, assuming it for M minus 1 and all smaller values. It doesn't matter how you do that. Let's do it where we're assuming it for M minus 1, M minus 2, and so on. And prove it for M. But when I say it, again, I really mean three assertions. Let's check all three of them hold for M if they were true for the smaller values, M minus 1 and minus 2. I'm ignoring the chat, pardon me. Okay, yeah, I think this is what it's going to come down to, right? Let's see if that happens. F sub 3M, right? I'm supposed to check that this is equal to an even number. And we have recurrence that says, oh, that's the previous value plus not previous, but previous, you know, two previous, right? And this thing, right, that's a 3M minus 1 is going to be the form of the form 3M prime plus 2 for some smaller value of M prime, right? If you want, I could write this as, just to be completely explicit, this is 3 times M minus 1 plus 2, right? It's got a remainder of 2 when you divide by 3, and that's the key point. The other one is F of 3 times M minus 1 plus 1, right? It has a remainder of 1 when you divide by 3. And so this thing is, what do we say, odd by induction. Right? This one is odd by induction. And so if we add an odd number to an odd number, we get an even number. Seem okay? Questions? And maybe I won't do all three cases. We still have to, we just check this one in the inductive step. Let me check this one, and I'll leave it to you to check this one for the F3M plus 1. All right, use the recurrence to say, oh, that's F3M plus F3M minus 1. In other words, the sum of the previous two values. F3M is, we just decided was even. Actually, let me do this. Say, rewrite this guy as F3 times M minus 1 plus 2. This one is even. This one is odd by induction. And maybe we should be careful. It's not that this guy was even by induction, but he was even by the case we just did. So it's good we did it in that order. But then the point is even plus odd is odd. And that's where it's supposed to show in this case. Pretty good? Questions? And before we write the end of proof symbol, F3 plus 1 case is similar. Any questions before we move on? So what's the point of chapter 4 is just more things about the Fibonacci numbers that you can prove by induction, but then some things that use other techniques. In particular, we're going to get a formula, actually, an exact formula for the Fibonacci numbers, which is kind of remarkable. And I'm going to do it in a way that's different than that of the book, because there are many methods that work to prove it, but I wanted to illustrate this method of generating functions, which I mentioned earlier as a counting technique. It's slightly more sophisticated. This is the first case where it's really, really effective, is getting the formula for the Fibonacci numbers. I don't want to go there yet, though. I still want to do some more things that we can prove via induction. So any questions before we move on to the next thing that we can prove inductively? Okay, so let me actually go back to our list here. And so we had this pattern of even, odd, odd, even, odd, odd, right? And so that's the question of whether you're divisible by 2 or not, right? Even ones were divisible by 2, odd ones were not. What about this fact? Did you notice, was anybody surprised that F5 was equal to 5? All right. And F10 is 55, and F15 is 610. Did you notice these multiples of 5 subscript Fibonacci numbers? They seem to be divisible by 5. Let me just emphasize that. Maybe I will use the highlighter here. Yeah, let's use the blue highlighter. We only have 3 examples there, unless you count this one. I guess we can count the F0 is equal to 0, and yeah, that subscript 0 is divisible by 5, and the answer 0 is divisible by 5. So what my point here is, note if 5, should I use this division symbol? Yeah, I'm going to start using this division symbol. Divisible by, okay? 5 vertical slash m. Maybe I'll put this up here. Then 5 divides fm. That looks a little messy. Fm, okay. So what is that? The vertical slash thing is divisible, or no, divides into, not is divisible by, divides into, divides. Maybe that's what I want to say, divides evenly into. That's what the vertical bar is. Everybody good with the notation? So let's see if we can prove that. So we also guessed this proposition. F5m is divisible by 5. There's another way of saying that. Right? In other words, these are where the subscripts are divisible by 5. We're saying the corresponding Fibonacci number is divisible by 5. You see how that's what I was saying on the first page? And again, this one, you can prove it by induction. You have to kind of muck around. This is one where you play with it and you don't immediately hit right what's the right way to do this. But I'm going to prove it by induction. I've already sat and experimented on my scrap paper a little bit. So I'm hiding the wrong paths, the proofs that didn't work. Let's again induct on M. All right. Again, the base case, oh yeah, we did actually bother to check that base case M equals 0. Didn't mean to do that. In the base case, M equals 0. What are we saying? F of 5 times 0, yeah, is F of 0 is 0. Good, that's divisible by 5. But in the inductive step, you gotta really try things. And I'm just gonna, again, assume it for smaller n. And I'm gonna write F5M, okay, I'm gonna try to use the recurrence. I'm gonna write it as F5M minus 1 plus F5M minus 2. And so here's the game that I was trying to play. First of all, I knew that this thing was actually true, that it was provable because I had read it before. But what I'm going to try to do is keep using the recurrence on some of these F's, write them as sums of smaller ones. And what's going to make me happy is when I eventually get down to an F5M minus 5, okay, that I know is going to be divisible by 5 because the subscript is 5M minus 5. Well, that's 5 times something else. So by induction, that's divisible by 5. What I'm going to hope is that I can get the rest of the stuff with subscripts that aren't divisible by 5, but there's coefficients in front that are multiples of 5, like 5 times things. And eventually, you can do this. So this is the kind of mucking around that I had to do. You ready? I'm going to use the recurrence. Every time I use the recurrence, maybe I will, do a little 2 terms. I'm rewriting that as 2 terms. I'm going to rewrite this guy as 2 terms by the recurrence. And so I get F5M minus 2 plus F5M minus 3 plus F5M minus 3 plus F5M minus 4. And if you want, you can simplify that as, you can put together 2 of the terms. F5M minus 2 plus 2 times F5M minus 3 plus F5M minus 4. Okay? So you see what I'm saying? You do get some coefficients showing up, and I'd be happy when those coefficients are actually 5s or multiples of 5s. Because I'm just trying to show the right-hand side, the whole thing is divisible by 5. But I'll also be happy when I can convert that subscript to a 5M minus 5, where the subscript itself is divisible by 5, and I can use induction. And so, yes, I'm just stealing a glance at my notes to see what I did, when I was mucking around. I think I took this thing and wrote it as a sum of 2 terms. And what happened? I'm going to start combining the coefficients. When I write it as a sum of 2 terms, I get a F sub 5M minus 3 that combines with that 2 times F5M minus 3. So I'm going to get a 3 times F5M minus 3. What else am I going to get? I'm going to get a 5M minus 4 that combines with that 5M minus 4 on the right. And yeah, next thing I get is 2 times F5M minus 4. Okay, we're definitely not having enough room on this page. So let's copy what the heck we were doing here and take it over here. And don't put that thing there. But this I'd like to be a little smaller. All right, still not there. So I took the F5M minus 3 and applied the recurrence on that. What is that going to give me? 3 times f5m minus 4. Oh, which combines with the 5m minus 4 from here. Yeah, this is starting to be promising. Let me see what happened. And now when I combine terms, I think I'm done, actually. What happens is I get 3f5m minus 4, 2f5m minus 4 is a 5m minus 4. And what's left is this 3 in front of the 5m minus 5, but that's now achieved what I'm looking for. That's a subscript that's divisible by 5. So this whole thing is divisible by 5 by induction. And I don't care about that 3 in front. 3 times something divisible by 5 is still divisible by 5. And this one has a 5 in front, so I don't care what the f5m minus 4 looks like. All right, so this one's divisible by 5. And so we're done. And if you add two things that are multiples of 5, divisible by 5, they'll be divisible by 5. Everybody see how that worked? Question? Okay, but then people noticed something even more, you know, that generalizes. I mean, people just kind of went crazy with Fibonacci numbers once they started noticing things about them. Let's go back to our page of data. Let me take this over here. Our tabulation. So 5 is F5, and it divides, we just decided, F5M. And here's an interesting thing. We decided that who divides F3M? We decided that those things were even, so they're divisible by 2. And 2 is F3. It's sitting right there. And so people thought about, wait a minute, maybe when I take F something, Fm, it's divisible, sorry, Fk, maybe Fk divides Fk times m. Let's try it. What about 7? Sorry, let's try it again. F7, not 7 itself. F7 is 13. It's kind of a random looking number. And I'm going to ask, does it divide like F2 times 7? In other words, F14? I don't know. Is this F14? What? I've got F14 on my table here. It's a 377. And my gosh, it's true, you know. It's 13 times 29. So you might guess. You see where we're headed, guess. Fk divides F, where the subscript is a multiple of K. And I guess I want to assume what k is at least, I don't know. Am I really assuming anything for k and m greater than or equal to 0? So let's actually try to prove that. Theorem. More generally, fk divides fk times n. Again, that vertical is divides evenly into. And actually, in proving that, it's got a little messy. It's fk times m. In trying to prove this, it's actually the easiest approach is to prove something kind of interesting, another recurrence for the Fibonacci numbers. There are a lot of Fibonacci, other recurrences that Fibonacci numbers satisfy, or other Fibonacci recurrences. Okay, so again, people kind of mucked around trying to prove this. I'm going to show you one approach, uses a lemma, something else that you prove along the way and actually turns out to make it easier. I'm going to show you that for all a, b greater than or equal to 0, here's a recurrence. F of a plus b plus 1 is equal to f a plus 1 times f b plus 1 plus f a, f b. And I claim this lemma, it looks a lot like the Fibonacci recurrence. I claim that if we take, what is it, b equals 1, this turns back into the Fibonacci recurrence. There's a special case of this. Either I take a equals 1 or b equals 1, which is the original Fibonacci recurrence, but this is some more general souped up version of it. Let me show you why this lemma would imply the theorem before we actually try to go prove the lemma, which is not too hard. So that's my next step. Any questions before I do that? Next step is, how would the lemma prove the theorem? And again, it would let us prove the theorem by induction on M. And again, where am I going to take? I guess M equals 1 would be my base case. Maybe I should take M equals 0. I don't know. I'll take M equals 1, but I think M equals 0 would be a valid base case too. Then we're just saying Fk divides Fk. Well, that's true. And in the inductive step, the more interesting part is how we're going to use this lemma. What I'm going to do is, right, so what am I trying to show? I'm trying to show Fkm is divisible by Fk. I'm going to write that subscript Km in this form for a particular choice of an A and a B that works well. This is going to save me from the mucking around that I had to do with the F5. This is like somehow realizing that argument that we did with the F5 is going to be encapsulated in this step here. So I'm going to write, yes, how do I want to do it? As, okay, let's try it. The A, I'll tell you who the A and the B are. The A is going to be K times M minus 1. And so I am going to write this. No, let me do this. I'm going to write N, which is Km, as A plus B plus 1, where the A is K times M minus 1, The b is k minus 1, and the 1 is a 1. Okay, so let me just make clear who's who here. The a is the k m minus 1, and the b is the k minus 1. And then what am I trying to say? Fn is fkm is, right, fa plus b plus 1, if we believe the lemma. So this is what I'm saying, use the lemma. And write it as fa plus 1, fb plus 1, plus fa, fb. And now let's see who these people are. A plus 1 is k times m minus 1 plus 1. B plus 1 is just k, because b itself was k minus 1. On the other hand, A is f, let's see, A itself is k times m minus 1. And the B, I don't think I'm going to care too much. Let me just make myself some room. The B is k minus 1. But now the point is, in each of these two terms in the sum, in this term I've got an fk, and I know that that's, you know, divisible by fk, it's fk itself. And this one is an f where the subscript is k times m minus 1, so it's divisible by fk using induction. Seem okay? All right, and so how do you prove the lemma? I think I'm gonna leave that for next time, because one should actually take a look at the first couple cases of the lemma, like when a is 0, when a is 1, when a is 2. It's actually something that we'll prove by inducting on the a. We will prove it for all values of b, but we'll use induction on the value of a when we prove it. But I'm gonna do that next time. Any questions? All right, and before I turn off the recording, the other thing that we'll do next time is we'll start talking about formulas for the Fibonacci numbers using this notion of generating functions. And I should have also pointed out on the syllabus, our book doesn't discuss generating functions as a technique, but on the syllabus, there is a set of notes on generating functions by, I can't remember if it's Greg Musiker. I think it's Greg Musiker, my colleague, has some notes on generating functions if you want to read up the idea ahead of time. Any questions before we turn off the recording?